Ladies and gentlemen, welcome to your Chapter 23 lecture video on circuits. I apologize for a couple of things, most notably that the music didn't really pan out in the last video. I'd really like to have a little bit on the splash, but that's not happening. And also, there's a demo that I wanted to do here at the beginning of this, but unfortunately my demonstration equipment is on campus, and that is all on lockdown until further notice, because quarantine life. In any case, let's start with a really basic definition then of a circuit. Now if we go back to the root of the word, the circuit usually means something like a ring or a loop, something that you go around. And in physics, it's not really that much different. A circuit is a loop or a ring that electrons can move through. Pretty straightforward. Our phones, cars, computers, game consoles, everything are all electronics because, guess what? It's electrons that move through the circuits in them, powering our devices. Now there's this really goofy kind of ancient definition where we say that current is the motion of positive charges. And really, it's negative charges moving in the opposite direction of the supposed motion of positive charges. We know for sure it's electrons that do so, because if positive charges actually moved, then the copper atoms in a wire would gain protons and become a different metal, right? Become other elements. So clearly it's the electrons, because those are just outside in the orbitals and those can go freely in between atoms, that actually move around. And the lunacy doesn't end there. We have this notion of electric potential, this thing that we defined as the amount of work per unit charge, that the electric field can do. Sort of similar to potential energy per unit charge, if you want to think of it that way. Charges should then move from a high potential to a low potential like gravity, except that if positive charges are carried around a circuit, negative electrons would be standing still, and it's actually the other way around, right? Electrons would actually fall upward against gravity in that analogy, which is just ridiculous. So why is it that we keep around this sort of ancient goofy definition, even though we know that it's negative charges that move in a circuit? Why do we continue to model current as the motion of positive charges? Well, tradition mostly. And I think Rick said it best when he said, scientifically, traditions are an idiot thing. I'm not really a fan of the goofy, antiquated definitions if it makes learning more difficult. So let's just never mention this ever again, shall we? And realize that current is actually the motion of electrons moving around circuits. The rest of the analogies we make about the motion of charges in a circuit usually work pretty well, as long as we remember that electrons are what are actually moving around the circuit and move in the opposite direction of this fictitious thing we call a positive current. Current is defined to be, we usually use a capital letter I, current is defined to be the amount of charge that moves past, say, a given point in a circuit per unit time. So what is the SI unit of current? Well, the SI unit of charge obviously is the coulomb, the SI unit of time is the second, and so the ampere, or amp for short, sometimes we just use a capital A, the ampere is actually a coulomb per second. If the unit of charge is a coulomb, unit of time is a second, ampere is coulombs per second. We can think of current like the flow of water through a circuit, and in that analogy, we have a water made up of electrons, right? And so, if you have more water flowing through a circuit, you have more electrons moving through a circuit. That's current. So more electrons, more charges means a greater current. In that analogy, if we want to think of current as the flow of water, right? The volume or mass flow of water, then voltage would be sort of more like water pressure. Electrons can only move through a circuit when they are propelled to do so, right? When they're forced to do so. Charges want to flow from a higher electric potential to a lower one, generally, right? Kind of like falling downhill. Like moving from the high side of a battery, right? Usually you have a battery, it has like a little nub on it. That's the positive side, and that's the negative side. And so current goes that way from one side to the other, even though we know it's actually electrons that move the other way, right? But a tangled web we weave. So electrons can only move through a circuit when they are propelled to do so. And for charges to keep flowing, the potential difference, this 1.5 volts that the battery has to keep between its terminals, has to stay constant. Now, a common battery like the AA or the AAA, the C cell and the D cell, actually, they're all 1.5 volts. They usually dissolve lead in acid and use the energy from breaking the chemical bonds in order to keep the electrons moving in a battery-powered electronic device. Obviously, this one battery, or maybe several of them, right, power the entire device, a whole set of circuits where the electrons continue to move. Thus, this voltage is applied across the entire circuit, right? It moves the electrons here, 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 and it forces them all to move together. Some elements in a circuit may use up some of the electron's energy and radiate it as heat. This is like a light bulb, right? This is usually because the tungsten filament, for example, in an incandescent light bulb, is resisting the flow of the current through it. I'm going to draw you a schematic. Usually we don't draw batteries by drawing a whole battery. We draw a battery like this. So this is a battery, right? The longer side, this is the positive side, this is the negative side, and the electrons actually go this way, but we model the motion of current the other way. In any case, so let's say we have a very simple circuit where this is what we call a resistor. A resistor, of course, is like the tungsten filament inside a light bulb, and indeed, this kind of looks like the spirally, springy-looking filament inside the light bulb, right? Now, what's going to happen as the current flows around this circuit is the current is going to have to go through this circuit element, right? Through this resistor. And because this resistor does what it does and resists the flow of current, it's going to be taking some of the energy out of this system, right? Away from the voltage, the battery. And in so doing, it's going to heat up. And as it heats up a bunch, eventually it'll give off light, right? Which is why if you put your hand near an incandescent light bulb, you can feel the heat coming from it. In any case, like I said, this thing here is called a resistor. And common examples of this are, of course, things like light bulb filaments. As the bulb absorbs energy, it gives off heat and light. The SI unit of resistance, like this, is this thing we call the ohm. Now, there's a simple relationship that governs the relation in between a voltage source, a current, and a resistance in a circuit. We call it Ohm's law, and that's voltage is equal to current times resistance. That's Ohm's law. Let's just do a couple of example problems, shall we? I'm going to leave a little bit of room here for us to do our calculations. But I'm going to write Ohm's law up here at the top just so we don't lose track of it. Okay? Now, let's say that you have a resistor. right, of 60 ohms. And let's say that you have a voltage source of 12 volts. So here's our voltage source, V, and here's our resistor, R. We want to know what the magnitude of the current in this circuit is. Well, we said voltage is current times resistance, right? Now we know what that is. We know what that is. We want to isolate and find the current then, right? So what do? We isolate by dividing both sides by the resistance. Sounds like some kind of dystopian sci-fi movie. Divide the resistance. In any case, that leaves us with the expression that if we divide the voltage by the resistance, we should get the current. Our voltage was 12 volts. Our resistance was 60 ohms. Thus our current, 12 goes into 65 times, right? We've got 1/5 of an amp, or about 0.2 amps. Pretty straightforward, right? Okay. Now let's say that we wanted to change the game just a little bit here. Let's say we wanted to figure out the resistance in a circuit where we have a light bulb that draws 12 amps of current in a 120 volt circuit. Okay, we got 120 volts of battery and we've got 12 amps of current. How big is the resistance? Well, we're looking for this one now. We have these two pieces. This time we're going to divide both sides by the current, right? The voltage that we have is 120 volts. The current we have is 12 amps. That means we have a resistance of 120 volts over 12 amps. That's supposed to be 12, I apologize. My handwriting is not good right now. Okay. In any case, 120 divided by 12, that's 10, right? And so the resistance in that circuit is going to be a grand total of 10 ohms. Now, why did I take the time to do this? Well, because if you're going to be solving one of these on your homework, on an exam, something like that, most likely you're going to be given two of these and have to find the third one, right? Obviously, if you get the current and the resistance, you just multiply them together to get the voltage. But if you get one of the other two that you have to look for, if you're looking for either the current or the resistance, you just isolate it by dividing, right? Pretty straightforward. Now, just for context, the Van de Graaff generator, that silver sphere that gets charged up by the little metal comb dragging across it, basically stealing the electrons from the surrounding environment and forcing them onto the sphere. They're not dangerous, even though the voltage can get really high. Sometimes you can get, a couple 100,000 volts on one of those things, a really powerful one. And it can give you enough of a static charge that, like, your hair will stand on end. Funny things like that will happen. But they're not dangerous because the amount of current that they can shoot through you is tiny. Most biological systems like us can withstand a certain amount of electricity, and as a matter of fact, if it were not so, we wouldn't be able to move, think, and breathe because our nervous systems are really good at sending electrical impulses. There's a little electric node in your heart that makes it run. It's a thing called a pacemaker. And if you have heart problems, sometimes you can get a little electric implant, an electric pacemaker, that helps your body regulate your heartbeat. However, If you get just a tiny little amount of current, something like 70 milliamps across your heart, it will fry your pacemaker and you will die. 10 milliamps, like what you get from a taser, is generally enough to knock you out just by sending an overload of signals to your nervous system. But don't worry, your body doesn't conduct electricity as well as most things that we use to conduct electricity. While it is true that your skin can conduct electricity a certain amount, which is why the field effect detector demo that I wanted to show you actually works pretty well, it's not nearly as good as things like metals. So you have to be either really naive and inquisitive or really stupid to electrocute yourself, or, want to electrocute yourself. That being said, make sure you turn off all the breaker switches in your house before you try to replace a fuse or rewire a socket or put in a light fixture or something like that in your house. Current moves through a circuit basically instantaneously, seeming to move around at the speed of light. And it really makes a whole lot of sense, right? That electricity moves at the speed of light, kind of like, lightning does, right? Very, very fast. However, would you believe me if I told you that the individual electrons in a circuit actually move at closer to about a centimeter per minute, very slow? Remember that current is the movement of a certain amount of charge per second, right? Remember, the ampere is coulombs per second. I want you to think about how many electrons that are in a wire compared to how many actually move. Now, if you have 1 amp of current, that's 1 coulomb per second that moves past a given point in some kind of wire, right? Let's say you got a loop of wire, you got a battery here, right? Then the current is going to move around this loop of wire, right? Now 1 coulomb of charge, that's 6.25 times 10 to the 18 electron charges per second. But if you take 1 mole of copper, 63 grams of copper, that's not a whole lot, right? That's, a little bit of wire. It's going to have 6.02 times 10 to the 23rd, right? 1 Avogadro's number, or 1 mole, 6.02 times 10 to the 23rd electron charges in it, right? Or actually just this many atoms, and each one of those is going to have a ton of electrons in it, right? Remember what the atomic number of copper is? Well, there should be that many electrons in each atom, right? Now, let's say that each one of these copper atoms has something like 10 free electrons in it. That means that there's something like 6.02 times 10 to the 24 free electrons in that wire that can move, right? So if we want to look at the difference between 6.25 times 10 to the power 18 and 6.02 times 10 to the 24, that's 6 orders of magnitude, right? 1, 2, 3, 4, 5, 6. So you're talking about there are 1,000,000 times more electrons in a wire, in just a little wire, 63 grams of wire, than there is current in that wire. So only 1 in 1,000,000 electrons actually at any given time is really truly contributing to that current. How can that possibly be? Well, electrons don't just float around, right? They have to go in between the atoms, the copper atoms in a wire. And so sometimes an electron will go from this atom over to this atom here, right? And then it'll just kind of sit there for a really, really long time. Maybe, not for many seconds. Maybe, not for minutes even. Who knows? But in any case, it may just go here and sit there. It might move at an angle. It might even move backwards a little bit, although generally that doesn't happen as much, right? And so if you take the average distance that an electron travels, actually physically travels, during the motion of current, we say that electron drift velocity is something like 1 centimeter per minute, the average distance that an electron actually travels. Now, why could one of these things actually move backward? Well, if one of these electrons collides with another electron, right, it can get ricocheted and move backwards, although it doesn't happen as much. But it happens a non-zero amount, enough that we should be aware of it. Now, there are generally, basically, two kinds of current. The kind of current that you get from, say, a battery or something like that is what we call DC, or direct current, right? And if you wanted to plot the amount of voltage over time that you get from a DC source, it's just like a flat line, right? This would be like your 1.5 volts that you get from your battery. It doesn't change. And as a matter of fact, this DC, or this direct current, is what all of our electronics use. However, I know that you've all seen the electronic plug, right? Some of them have like the 3-prong thing. These are all AC voltage sources. And what an AC voltage source is, so sometimes it's positive, sometimes it's negative, right? And it oscillates like a sinusoid, like a wave. Well, wait a minute. If all of our electronics use this, how is it possible that we can take this source, this alternating current or AC source, and make it into that? Well, we want to try to make this into a flat line, right? So, this is what we're going to do. We're going to be really clever, and we're going to use a couple pieces of technology, one of which is this diode. Remember what a diode does? It only allows current to go one way, right? Okay, so we're going to take a diode, actually several of them, and we're going to take this other funny thing called a capacitor, which stores charge. That'll be important later. So, let's say we have over here an AC voltage source. That means sometimes the current is going to go this way, right? Because it's like a wave. Sometimes it's going to be positive and go this way, and when it's negative, it's going to go this way. Okay? All right. Now we're going to make a nested system of diodes. A bank, if you will. In the middle here, we'll have another diode, and in parallel with that, we'll put a capacitor in just a minute. But for right now, let's just put in these diodes here. Now, I'm going to get the other colored pen, and I'm going to draw the negative current down here, this in red. So when it's negative, I'll draw the current going the other way, okay? Now, when the current is positive, it's going to go this way. So it's going to go here. Now, it can't go this way, right? Current only goes one way through a diode. So we're going to go this way, and then we're going to go across this diode, and then across this diode, and back this way to complete the circuit. Now, when it's negative, we're going to go in the opposite direction. So we're going to go this way. We can't go this way, right? So we've got to go here. We're going to go back across this diode, and here, and across the circuit. Now, if we wanted to look at the current that goes through this diode, what's it going to look like? Well, it's always going this way across the diode, right? And so if we wanted to plot out what the voltage looks like over time, this is from the AC source. And at our diode, it's going to be like this, right, when it's positive, like this when it's positive. And normally, this part down here, right, this part that's negative, it's actually going to go straight across it instead, right? And so the wave becomes rectified. We only get positive current. We always get current going the way that we want it to. Now, there's a problem here, right? Our electronics need this DC signal, a constant voltage. And so what we do is we put a capacitor here in parallel so that when this gets charged, it takes some time to charge, but it also takes some time for it to discharge. And so what that does, instead of it dropping off, it flattens this part of the curve, like what we're trying to do with the COVID virus, right? And then it'll charge up a little bit, and then discharge. And then charge up a little bit, and then discharge. And so that looks a lot more like a flat line. And that is how we take one of these AC waves and rectify it into DC current. So we call this a wave rectifier. We call putting in this capacitor filtering the wave signal. So this is a filtered, rectified AC wave, right? We get this DC signal from an AC source. Now LEDs, while they are diodes, right, and they make light, they aren't the only devices that make light. We can use fluorescent light bulbs, like those terrible things we have in the classroom, to make lights, or we can use incandescent bulbs, things like that. Old light bulbs, like the incandescent ones, usually have a tungsten filament in them, like we said, where heat generates as the electricity passes through it, heating it up and giving off light. We measure how much energy they give off per unit time with a unit that we're probably familiar with by now, right? Everybody remember what the standard SI unit for energy per unit time is? Power, right? That's energy per unit time. And as usual, the unit for power is the watt. So the amount of energy that, or light energy in this case, that something like a light bulb or whatever gives off is the amount of energy per unit time that it radiates. And so if you look at a light bulb or something like that, it'll tell you its wattage, right? That's how much actual energy it gives off per unit time. Now, for our context, power is also equal to current times voltage. Now, I really wanted to pose a question to you about having a circuit with several light bulbs in it, but unfortunately I don't have a bunch of light bulbs that I can string together with a series of batteries. All the equipment for that is also in the lab back at school. But I have included a video about series and parallel circuits and the light bulbs in them. Really quickly, however, let's say you've got a voltage source like a battery and you have a bunch of light bulbs in series, right? You have one resistor and another resistor and another resistor here, right? And as the current goes around the circuit, it's going to light up all three of them. Now you only have one voltage source lighting up all three of them. And so it may not be super bright compared to, let's say you have a voltage source here, and you have 3 light bulbs or so, what we call in parallel, right? So there's a loop, a separate loop that goes to each one of these light bulbs. That makes its own circuit with each one of these, right? Now because of that, these generally are going to be much brighter. About as bright as if you just had one light bulb in a series circuit. Why? Well, if you think about the electrons, right? This electron gets here, it has more than one place it can go, right? Same thing when the electron gets here, it has more than one place it can go. And because these electrons have more possible avenues that they can follow, more electrons can actually move through the circuit. That means more current is going to move through the circuit, and it's only each one of these circuits individually is limited by the voltage, because remember, according to Ohm's law, voltage is current times resistance. And because each one of these light bulbs basically has its own circuit, they can be just as bright as a circuit with a single light bulb in it. Long story short, the light bulbs in a parallel circuit are generally brighter because they have their own access to the voltage source. The drawback is it'll draw more current from this voltage source, and so it'll wear out your battery faster. In any case, this is a really good time to go ahead and view the series and parallel light bulb demo. I hope you've enjoyed your Chapter 23 lecture.